Welcome back, everybody. So today I'm going to go over this our new lesson, analysis of algorithm. So here's my promise. So I'll cover the concepts, problem, algorithm, and program. I'll explain the analysis, why the analysis of algorithm is crucial. I'll explain why the explicit comparison is not reliable. I'll explain a way to formulate a standard symptotic analysis. And then I'll demo uh, some of the mechanics empirically in a program, and then we will formulate a big O, big omega, small omega, and big theta notations. And then I'll discuss storage as a resource of interest. Then I will end the discussion with a review of some misconceptions about analysis. So let's start. So let's talk about what is a problem for for now. So it's basically a setup or it's a task to be performed. So it basically a problem matches set of input to an expected output according to set of constraints. Okay, those constraints either given or stated or implied. So once the problem is well defined, then we can solve that problem. Okay. So problems in mathematics, we can represent problem as functions. Like for example, y equals fx over here. So input is coming as x and basically govern the parameters or the domain, and the output y, we call it range. Set of parameters of a problem is called an instance of the problem. Okay, so for example, sorting a given array um, is the given array here is the set of parameters. Okay, so so it's basically uh, uh, a particular problem when we have given the set of parameters. Okay, so we call it an instance of the problem. All right. So one problem instance always give one output. All right. Let's talk about what an algorithm is. Okay. So algorithm is a recipe or a method to solve a given problem. Okay. And there are a bunch of synonyms that are closely and loosely related to each other on algorithm. Say, you can tell it's a method, a process, a recipe, a bunch of steps, a plan, or pseudocode. Okay, so usually we use plan and then pseudocode most commonly. Okay, so so that's an algorithm. Okay, basically it implements a function transforming input to output. So basically it governs a set of steps how we transform the input in our problem to get the output. Okay, and a given algorithm only solve one problem. Okay, and on the other hand, there could be many algorithms to solve one problem. Okay, one algorithm solve only one problem. There could be many algorithms to solve one problem. For example, sorting. We already know there are a bunch of sorting methods like selection, insertion sort, selection sort, bubble sort, quick sort, merge sort, all those. An algorithm must be correct. and it should have well understood steps. It must terminate as well. It's not always right. For example, an operating system probably runs algorithm until we turn off our computers. Okay, but usually an algorithm must terminate. Okay. All right. So let's talk about what a program is. So program basically implements an algorithm. Okay. So is an basically it's an instance, okay, um, or representation of an algorithm in a particular language. Right. So, for example, solution in a programming language of an algorithm is a program. Okay. All right. So there could be many programs that solve or implement one algorithm. Okay. So algorithm and programs, two different things. So we should avoid to use them interchangeably. Okay. So then let's talk about why analysis of algorithm important. So one first thing, we have a bunch of algorithms, then we need to pick which one is the best. Okay. So in that regards, we need to find the best performing algorithm. So let's take an input size n. Then we need to ask the question, okay, what are the features that determines performance of an algorithm? Okay. So what features can we use to judge the performance of an algorithm? So the first thing is time, right? Obviously, we want the algorithm that takes the least amount of time. Okay? So the running time is one. So we know that t varies with the input size. Okay? So that means the time, the running time, is actually a function of n. Right? We also know that space also valuable resource. So you can use space also has also to measure the performance of an algorithm. Okay, so it's not that space is not that critical compared to time. Time is the most critical resource. Space every day the space is getting cheaper by the day, so it's not that critical. But if you, let's say, if you want to program a chip or a CPU, then the space is a critical commodity. Okay, so not always, but there are situations in which the space is important compared to more important compared to time. Okay? So if we take that as S, and we know that space also depends on the input size, so we can say S also is a function of input size. So here it's Gn. So this we need to strike a balance. Some many algorithms depend on both space and time, and sometimes it takes less space but more time to run. Sometimes it takes less time but take more space to run. So that we need to basically strike a balance between space and time. We call it space time trade-off. Okay. So again, some run fast but need more space. Some run slow but need less um, less place. Okay. So basically we need to keep a balance of things. So we're gonna go over this topic in detail later in this lesson. Okay. So all of this requires solid comparison criteria. So then how do we compare them? The next question is, okay, so we should, then how do we compare them? So one way of doing is we can explicitly run them and measure time, how long will it take to run. Okay. Then the question is, what affects running time? Is that only the algorithm or there are other factors here? So obviously the algorithm uh, um, affects running time, but which is the one we want to measure. But is algorithm is the only factor? Is the question next to us. The answer is no. So it depends on program quality, right? It depends on the computer itself, the platform or the infrastructure we test the algorithm. So that means the CPU, the peripheral hardware, and other hardware as well. It depends on the resources we have. So how amount of memory or the storage or the network. If our algorithm interact with the internet or the network, then network also it depends networks as well. And the environment, the operating system, the compiler, the programming language of implementation itself. Okay? So there are many factors involved in running a program and measuring the running time. So that means it's not reliable because the running time doesn't only depend on the algorithm. There are a bunch of other factors as well, and there's now bias. So then let's imagine for now we normalize these other factors. Would it still unreliable or reliable? Okay. So why if not? Why if it is still unreliable? Let's see what are the reasons. Okay. So first is effort. Okay. So to compare running time of two or more algorithms explicitly, you'd have to implement all those algorithms, and then that requires some effort. And there's implementation bias, right? For example, one of the algorithm, uh, uh, the best engineer writes one of the algorithm, implements one of the algorithm, a not so good engineer implements the other algorithm. So now there's the bias from the engineer. So one engineer used best strategies to in writing the program, the other same algorithm, and the other engineer use the different like not so standard tactics to write programs. So now there's the programmer bias, and in some of the test cases may be unfair to one of the algorithms, and others are not. So that there's now testing bias. This could be by budget as well. This is not just the time or money or anything. Resource, like for example, memory usage. So those would not be fitting to one of the algorithm would not be fitting to the resource budget. So now we have a problem of implementation. Okay, so that means we need a better solution. We need to approach this in a different perspective. And that means basically we need an independent model of all these biases. Okay. So this suggests that we somehow need a theoretical approach to this problem. And that theoretical approach require a model, and we call it a random access machine model or RAM model. Okay, and then it comes with bunch of assumptions. Now let's go over them. All right. So a single instruction or a step. is called simple or basic or primitive operations. Okay. Simple math like addition, subtraction, division, multiplication, modulo, comparison, like relational operators greater than or equals, equality, less than, and then selection like if else, conditional check, and then call like call to a function. Not I'm not saying the body of the function, just the call to the function. And then array access, memory access, pointer dereference. They are all simple operations. So basically, they take one time step. Okay. So loops and function body, they consist of sets of simple operations. So that so loops and functions doesn't have like they consist more than simple operations. Okay, they are sets of simple operations. Simple operation take constant time and they independent of operand. So this is really important. Okay, so simple operation take constant amount of time and they all are independent of the operands they operate on. So if we take this example, multiplication between two numbers, we have um, two operands, 2 and 10 over here, and then in between we have the multiplication operator. So, and in here we have 20,000 and 10,000, so the multiplication. So the model assumes both these operations take same time, okay, and it's independent of the operands, okay. So we know that this is a strong assumption actually, and if the operands are really large, we know that it takes a bit longer time to run in a multiplication. So we need so we basically so that's a bit of a strong assumption, but that time difference you will see that we can easily neglect in this theoretical uh, development of framework. Okay, so we see that this is a fairly reasonable assumption to make uh, in uh, in assuming okay, so these times are same. Okay, though they are not actually exactly same. So what I'm saying is that difference is negligible. Okay, and we'll see that. So there's no concurrent execution. So, but it's another assumption is that so so basically a single program runs from top to bottom and one after the other. So each one step and then the next step. So we execute. There's no simultaneous execution of two or more steps, and the memory is unlimited. So there's no um, limitation of memory. So that means memory access is uniformly available. Okay. For example, this is also not true. Like there's no unlimited memory for a machine. For some like machines, once up to the memory is up to one level, and we know that the machines start swapping, like meaning trying to use the hard drive as a resource of memory. When that starts happening, we all know that the computer gets really slow down because access to disk is really slow operation. But it's a reasonable assumption to me. All right. So let's talk about um, in formulating this independent standard, and then we're gonna basically now talk about this concept called asymptotic analysis. Okay. All right. So if we take this number of simple operation, m amount of simple operation, if that takes t, then based on our assumption that we made earlier, then t is proportional to m. So that means m is a measure of t. Okay? So simple operation, number of simple operation is a measure of t. The reason is one simple operation take constant amount of time. Okay, so t is proportional. This is the proportionality symbol to m. And we also know that m depends on input size. Okay? So size n. So m is now a function of n. So m equals tn. Okay. So that makes basically t equals fn. Okay. Because m is a function of so t is a function of m. So then t is a function of n as well. Okay. So we say t is a function of n, and then we represent that as t of n. So tn, and we call this time complexity of the algorithm. Right? Tn, time complexity of the algorithm. So by figuring Tn, we may be able to predict T, the time, without measuring it. Okay? So we may be able to, it's not an exact analysis, but we may be able to predict this Tn and then even make conclusion on comparison of algorithm based on that measurement, that prediction. Okay? All right. So next question is then, do algorithms have behave uniformly? Okay. So the answer is no, right? So if you take for an example, if you take linear search, okay, so looking up this 7, which is sitting at as the first element, takes only one step, okay, and that independent of size n. Okay, so if we take this array, it takes just one step. If we have the array with million elements, and if still 7 sitting as the first element, then it still take one step. So it's independent of size now, right? So if we want to look up 9, okay, it's linear search, so it takes in here 6 steps. But if our array has million elements and then still 9 sitting as the last element, then it will take million steps. So that means basically looking up 9 depends on the size. So that means algorithms do not behave uniformly. Okay? So let's then talk about this average case. So the average, basically average case governs the average inputs, the behavior of the algorithm on an average input. Okay. So basically average input gives the average time. Okay. And it's dependable analysis. Okay, so basically, if we can say on average this is the way, it's really dependable because we know that input can vary. Okay, so basically it covers the most post probable scenario, okay, input scenario. So in that regard, it is the most desired analysis. Okay, but it's hard to figure out. You need to basically consider multiple input scenarios to get the average. So it may even need a statistical analysis. So let's talk about the best case then. Okay. So basically, the best case means the input that giving the best running time. Okay. And it's not general, so it's less common. Okay. So it's usually a corner case, but it's easy to figure out. But it's not dependable. We cannot rely on the best case because it's a corner case. But it is the most desired dependable. Everyone tries to achieve the best case of the algorithm. Okay, so it's the most desired but not dependable. So if we take the linear search, the best case is when the search key locates at the start of the array. So in here, searching 7 would be the best scenario. So let's talk about the worst case. It's basically the the case input situation that's giving the worst running time. It's again not the general scenario. It could be a corner case and it would be easy to figure out as well. But again, it's um, least desired. Okay, so we don't want the worst case running situation on an algorithm, but the analysis is dependable. For example, if we can cover the worst possible scenario, then we can guarantee our algorithm is the analysis complete for the worst possible scenario. So, and we know that it's a corner case, but it's and then the rest of the instances, rest of the scenarios would run faster. So it's a complete analysis in that case. So in our analysis throughout this class, we usually go for this analysis. Okay, all right. So basically, if we take an example uh, of linear search, then when the search key located at the end of the array situation would be the worst case scenario because we'll have to check all the elements all the way up to the end, and then that's when we gonna find it. Okay. Or the other scenario is obviously when the search key is not there. That's also a possible worst case scenario. Okay. So we have to check all of it, but it's not found. Okay. All right. So let's now uh, um, demo this. Um, let's use a specific problem, in this case selection sort, to come up with a strategy or postulate a strategy in formulating a framework. Okay, so let's analyze selection sort. Okay, so here is the step algorithm for the selection sort. I just copied it from our book. Okay, so those are the steps, and each step has a cost. So this is a table of steps, cost, and how many steps. Okay, so cost of single step is here in this column, and how many such steps or operations in the last column. Okay, so the first step is okay. So it's a function. So we call the function. So that's cost is C1, and then just one. When you call one time, just one call. So number of operation is one. And then there are two for loops in selection sort. I highly encourage you guys to take a look at the algorithm in chapter 8. Right. So basically what we do in selection sort is um, we look for the next big index, and then once we find the next biggest item, we basically put that at the end of the towards the end of the array. Okay. So then selections for selection sort, the worst case analysis is when the worst case scenario is when when the input array is already sorted. When that happen, basically all the all the required comparison all the way up to the end of the array going to happen. Okay, so that means for selection source, worst case happen when we have the array already sorted. Okay, so this is that example actually. Okay, so we are basically um, sort of trying to um, trying to predict the worst case scenario of the selection sort. Okay. All right. So first, uh, first for loop. Okay. So it runs from I from 0 to n minus 1. So that means there are n minus 1 operations. Okay. So this means that basically every time this program and check this for loop, and how many of those checks? N minus 1. Okay, because you know that there's a conditional check in every iteration of a for loop, whether this I reach this n minus 1 or not. That's the check. So every time for loop runs an iteration, it comes back to the for loop header and check for that. And then how many of those checks? N minus 1, because we run from 0 to n minus 1. Okay, and then we go inside, and then when we basically assign big index to 0, and then we need to find that big index. So that actually so it runs inside the for loop how many times again? N minus 1. Okay, and then we run inside the other for loop, inside the inner for loop. So that runs from 1 to n minus I. Okay, so so there are three such checks. So for that, basically, how many times this check happen? For the for loop, it's n minus I times, and then the whole thing runs n minus 1 time. Okay, so basically what we have is that first, if we take the I equals 0 scenario, which it's basically inside loop going to run 1 to n. Okay, so since it's 1 to n, we have n minus 1 many operations plus, and the next iteration I is 1, so it's going to be 1 to n minus 1. So that means n minus 2 operations. So we need to sum up all those, and it's going to end up with plus 2 and plus 1 likewise. And if you sum up this summation, you're going to end up this one. Okay. So so basically, and then I'll post a proof to this this summation as opposed to the video quiz. Okay. All right. And similar amount of iteration for this check. Okay, to find the big index. Okay, and that's also similar to this one. And then the assignment of big index. If this is true, and this assignment, this check also runs n minus the same amount of time. Okay, so so this means basically, and then at the end, what we found the j. Okay, we found the big index, and then we're gonna swap the big index and the the one next to the last item. Okay, from the end basically. So we are putting the biggest value at the end. So that's how many times we're gonna do that? N minus 1 time again. Okay. So what we need to now do is we need to sum up these values, and then find the time. Okay. So the total cost. So this is cost per each simple step, and this how many of them we have. So we need to multiply each one, and then each cost per simple operation, and multiply how many of such operation, and then sum up all of these, and we get this expression. Okay. So it's basically this right here, constant A, and this right here, constant B, and this right here, constant C. Okay. So okay. So so let's analyze the selection sort. Okay. So before that, I'm going to demonstrate to you how we can do this in our program. Okay. So I already written this code. Okay. So in here I have the selection sort implemented. I simply followed the algorithm and then wrote the code. Okay. So we have a vector and then we are passing that vector and then a sort. Okay. And basically it's in place sorting mechanism. So we get the sorted vector. Okay. And in the main program, I call the selection sort and then measure the time between. So this is the starting time t1 and then the ending time t2. We measure that and then the time difference. So I basically then print the input size versus the time difference. Okay. So in here I initialize the vector for each input, and that's why I am clearing it at the start and then adding values. And notice the way I add value, it's in the sorted order. So I start from one and then add values one after the other. So the array I will receive is actually a sorted array. So so that is to make sure basically basically make sure array is sorted. Okay, so vector is sorted. Okay. So and then we apply section sort and then we measure the time. Okay. And then let's run this one and get the bunch of data points and we can plot it and then we can fit it. Okay. Notice I'm printing it in nanoseconds. Okay. So this is what I get. So I'm going to copy this and then I'm going to go over here and I'm going to get a new one. Right. Just paste it there. Okay. And then I'm going to make I'm going to fit it. Okay. So y1 as equals a. That's what the sort of the analysis we came up with, right? A x1 to the power 2 plus b x1 plus c. Okay. Now we don't need the negative values. So I'm gonna do this way, and I'm going to quickly do this as well. Arrows and then put this, and this is n, and this is tn, and that's actually in nanosecond. Okay, all right, and then yeah, and then I can actually uh, shorten this as well. So I'm gonna do this to 20,000. Okay, and here also um yeah, let's see, 110 to the 9. Okay, yeah, there you go. Okay, all right. So you can see that it's a really nice prediction, and if we take a look at our feed, and it's really close to 1. If r to the power 2 is 1, then we know that it's a perfect fit. So it's really close to 1. So that means it's really close to it's really perfect fit. And we can plot the residual, and you can see that right here there's a deviation, and other than that, it's really good fit. So And we proved sort of that we empirically tested our selection sort algorithm for the worst case, and we came up with this pattern. Okay. So that is to say, it's we can do this and then check for ourselves, but we cannot rely on um, testing like this. And I explained it earlier, right? Okay. So let's go over selection sort analysis. Okay. All right. So Tn. So we came up with this fit. Okay. And A is a constant, B is a constant, C is a constant, and they all depend on the system. And then we just found out particular A, B, and C for my computer. Okay? And then that would be really different for you. Okay? So that is to say, yeah, that's why we cannot rely on them. Okay? So they are useless for a general comparison, right? Across like theoretical across just to compare the two algorithm, we cannot rely on those A, B, and C. Sorry, I'm saying here. Okay? So we need to base sort of the idea of this, the growth or the rate of running time, the rate of growth, rate or the order of growth. Okay? So for larger n, okay, so we can simply leave the smaller terms. Okay, so we know that for because in this function grows into the power 2, so when n grows really large, we can simply ignore these two terms. Okay, because the significance of those is really minimum. So we can simply take it as this, right? And then we can ignore A as well. Okay, so again, A depends on the system. So we can get rid of A too. Okay. All right. So basically, then what we left with the most significant term in the function. So we say the worst case complexity of selection sort is, here's how we pronounce this, big theta of n to the power 2. And yes, I agree that this is coming out of the blue, this theta, but I'm going to explain it later in the lesson. Okay. For now, I'm sort of immersing you guys with this. Okay. All right. So for large n, so we can use this theta notation for evaluating or making like overall evaluation of an algorithm. Okay. For example, for the worst case, we can say big theta of n to the 2 runs faster than big theta of n to the 3. Okay, right? We can clearly see that it's basically um, this compared to this big theta of n to the 2 runs fast. It takes less time. Excuse me.